In this video, we're going to talk about chemical kinetics, and specifically, we're going to look at reaction rates. So chemical kinetics is the area of chemistry where we look at reaction rates, and we also look at the sequence of steps that reactions occur by. So when we see a chemical reaction, we often just look at the reaction, the overall reaction, but sometimes those reactions don't happen in one step. So we will talk about later on the sequence of steps that leads us to the overall reaction. But first we're going to talk about reaction rates. Reaction rate refers to the increase in the concentration of product or the decrease in concentration of a reactant. So we can look at it from either perspective. As the reaction progresses, we can look at how much the concentration of the product goes up, or we can look at it from the perspective of the reactant, looking at how much the concentration of the reaction goes down. So chemical kinetics, it really looks at how fast a reaction happens, how quickly that reaction will go to completion, or at least to equilibrium. So in the first semester of this course, we talk about thermodynamics and thermochemistry. Thermodynamics tells us whether a reaction will happen. It tells us if a reaction will happen at all. Kinetics is what tells us how quickly a reaction happens. So there are several factors that affect how quickly a reaction will happen. One is the physical state of the reactants. It's usually faster for a reaction that's in the liquid or the gas phase than it is for reactants that are in the solid state. So if we start with just liquid or gas reactants, the reaction will often proceed more quickly. Concentration of the reactants affects reaction rate, and we're going to look at specifically how that factors in later on. The temperature of the reactants. In general, a reaction will proceed more quickly at a higher temperature, although that's not always necessarily the case. And also the presence of a catalyst. We can sometimes speed up reaction rates using a catalyst, and we're actually going to talk specifically about that in another video. So we can look at reaction rates over time in terms of concentration. So for example, in this reaction, we have N2O5, which forms NO2 and O2. So we have time in terms of seconds, and we go from 0 to 700. If we look at the concentration of N2O5, which is our reactant, it is decreasing over this time period. And if we look at the concentration of NO2 and O2, those are both increasing because those are our products. So we're going to look at how that translates into a rate. So if we put this on a graph, we can look at this as the rate of N2O5 decreasing, or we can also look at this as the rate of NO2 and O2 increasing. And we can look at the slope over a small period of time and see the change in concentration over a certain period of time. So we can write the rate as the change in concentration over the change in time. So that's what this is referring to. When we have a reactant or a product in brackets, that bracket refers to the concentration, and we usually measure concentration in molarity. So this is the change in concentration, in this case of N2O5, and this refers to change over time. So the rate for N2O5, if we took from that table, if we pick the amounts at 400 and 300 seconds, if we go back to our table and we go to 400 seconds, this is the concentration, and at 700 seconds, here's our concentration. So at 400 seconds, our concentration is 0.0101 molar. And at 300 seconds, our concentration was 0.120 molar. So if we look at the change in concentration and the change in time, that gives us the rate of decomposition of N2O5. And this is negative because our N2O5 is a reactant, so it is decreasing over time. So that comes out to 1.9 times 10 to the negative fifth molar per second. So we can relate the rate of the reaction for the reactants to the rate of reaction for the products. So we will always have the change in the concentration of the compound that we're talking about over the change in time. To describe something that is decreasing, that is a reactant, we put a negative sign in front. And we put the coefficients as their reciprocal. So N2O5 decreases at half of the rate in which the other reactants appear. So for example, if we compare, at the rate at which other products appear. So for example, if we do everything in terms of O2, since O2 happens to be 1 molar, the rate of disappearance of N2O5 is going to be half the rate of the appearance of O2 over time. The rate of appearance of NO2 over time is going to be at 1/4 the rate, the concentration of the appearance of O2 over time. So if we do this in terms of a generic reaction, the reactants will always have a negative sign in front of them, and the products will always be positive, and the coefficients are always 1 over the reciprocal. So we can look at this in graphical terms as calculating the slope, which is essentially the tangent of a small part of the curve. So if we look at a small part of the curve, we can look at the rate at that particular point in time. So we're going to stop here and we will get into rate laws in the next video. And I will see you in class.